What? You're not even taking notes?
I learn better from.
I don't care. You learn the way I tell you need to learn, right? No, I'm kidding. That's perfect. I've got. What's that?
Just absorb and not like when you're lost. Like
I know. I've got multiple people in my first class that do that as well. But then they get pissed off because in that class, like you guys show up every day. You guys care. I like that. Okay. In the other class, I get maybe 30 out of 60 kids show up. So I gave them. I've got a rule, and I've been very lenient on it because I'm easy. But it's like, if I told them at the beginning of the semester, 40 out of 60 show up, I will post the lectures for everyone to enjoy. Right? We get like 35. Usually the class starts at 8. Have 30 there. By the end of class, I'll probably have like 38. And they just kind of trickle in. A lot of errands in that class. A lot of errands. Okay?
parking's terrible around here.
It is. You park in the back of Cobley. Don't you know this yet? Elias does it.
Barry and Elias, they don't let me do that.
You're not allowed to do that if you're not research.
Yeah,
it's only for
they let me do it
research
yesterday.
purposes.
It was a big step.
That was a big step. Be careful though, because we can get it taken away from us.
It's like
I only park there because a friend of mine is the head of facility services,
Yeah.
and so he says I can park there. So.
You just have to know if there's going to be something that, because people a lot of times are using that area. So
Yes,
if
for
you know
sure.
what's
Like the
going on,
labs, yes. If you know what's going
in the
on,
lab,
for sure.
then there's certain
For
times.
sure.
where it's
Or you
like-
just leave your keys in the car. Like Madison leaves her keys in her car. We decided that. So if you know what Madison drives, if you need a vehicle, go check it out. Okay. I drive an old piece of shit T100 Toyota. Okay. It's parked in the back of Cobley sometimes. Keys are in it. Okay. You need to run an errand, you just go for it. All right. You need it more than I do. All right.
Or if you just want to go get like food.
Go for it. Honestly, that would be awesome. Kind of. Unless I like went out to use it. Yeah. But usually Monday, Wednesday, Friday, it's here most of the day. But most of the time I park back there because I need it to go somewhere relatively quickly after this. Okay. So if the beam deflects enough, well, why do we care? Well, we don't really care about that because we are going to actually assume that the displacements are small, right? We deal with very small displacements. That allows us to do a few things. One is we can do equilibrium of the undeformed. And we're going to go through when we look at the deformed shape, okay? But we usually look at the equilibrium of the undeformed shape, right? P delta effects essentially would start taking hold, right? The fact that this displaces changes the geometry. The loading now P is imposing not only a transverse load, right, a shear in this member, but also an axial load in this member. And so things get more complicated. But if we assume the displacements are pretty small, then we don't have to worry about that. And because of them being small, bending and axial are uncoupled, right? We no longer have something that, right, the bending stress in this can be a function of the axial load, right? A big example of that would be a column, right? A beam column, for instance. Right, the column on the side of this building, it's got wind load sticking at the side of it, so it's bending it, so it displaces transversely. Then you have axial load acting on it also, right? So if you look at the undisplaced shape and you do the equilibrium, right, you did get no contribution of that axial load to the bending in that column. But the second you allowed it to displace, and then you sum the moments, right, and look at equilibrium, that point load now is going to try and further bend our column, all right? So because of all of this, we can just use superposition of our previous work. Right? We can take the bar element results we got and just add it to the beam element results we got. So now we get this element that looks something like this, which is now really close to VA, right? The only thing we're missing now is rotations and translations in the other two dimensions, right? The x-axis and the z-axis, right? So, force displacement. We end up with the same equation that we had before. We have our energy equivalent loads, which we'll talk about the homework here in a second. But now, instead of just having our transverse W sub x, well, now we have this surface traction, right? It goes along the length of our member that we need to incorporate. Okay. And what do those all look like? Right. Well, now instead of just having R1, M1, and R2, M2, now we have our axial forces, right? Or our axial loads at our two nodes, right? F1 and F2. Our displacement matrices, now we have a U1, not just a V1, theta 1. Now we have a U1 and U2 in there, so that's a 6x1. And then if we start imposing, right? Now when we do assembly of all of this, and we look at the stiffness matrices associated with having now 6 degrees of freedom, we end up with now overlaying our axial stiffnesses, right? Now we have to incorporate the EA over L that we had before into our stiffness matrices. Yes?
So then, yeah, on the homework, we're solving for the second part, that integral part after F essentially. Right?
Yes.
And we don't actually solve for those terms in it. Is it like we solve for like KD minus F?
I'll open it up and we're going to talk about it.
Okay.
We're going to open it up and we're going to talk about it. Okay, so what does this do with our shape functions? Well, now we need to incorporate, right, the shape functions associated with our axial degree of freedom, right, figuring out how our nodal displacement, now our U1 and U2, affect what's going on within the field, right, our interpolation. One other thing that we would like to do, right, is in VA, they couldn't sell a lot of software if we just were able to do beams along the x-axis. They all had to be straight, flat, connected, right? We got orientations to them. And so when we do orientations and we rotate things, right, we need to transform those. So very similar to what we did before, but now we add an additional, right, row and column. That allows us to make our transformation, right, from our, see, this is theta, right? This is equals, right? So our local forces, F1, R1, M1, and so on, equals our transformation matrix times our global degrees of freedom, similar to what we did in our bar element. And with that transformation matrix, we can use the same algebra that was done for the bar element to essentially establish a global, I'm going to say this F double bar,
What does the double bar mean?
it's global. Yeah, that's what this guy is. Global. Now we have our surface traction, our transverse load, dx equals global displacements. Right. And this was just followed the same lines as what we had, right? This is our global stiffness matrix. Same process we did with the bar element. But now this transformation matrix allows us to transform our transverse displacements, right, and rotations, and our axial displacement into global. Assembly, right, same is done for the bar. Right, but now we just have three degrees of freedom at each node.
Why are Q and W not together? Why are they like separate?
Because they act in two different directions. we're gonna have our shape functions, which are attached to, right, the U direction and the transverse direction, right? So we need to make sure we keep that split. So with that, that's where I was gonna get at. All right. Yes, Aaron.
What is an example of a traction force?
I mean, traction forces are as simple as like pounds per foot along the length of a member due to like a collector force. Like if you were in a building and you had wind on this wall, it's going to transfer either to the floor or the ceiling. It's going to run through this diaphragm, and that diaphragm is then going to impose that load right along the length. You guys went over that in like timber design, right? And masonry design a little bit too, I think.
Like siding would be like traction.
Yeah, I mean, if you were adding like, yeah, I guess you could look at that. Like on a plate element, you talking about siding? Yeah. Or like, I would see it as like girts or purlins in a like a pre-engineered metal building, right? Where those girts or purlins are hanging off of columns, right? So you have this essentially like a line load that you would then create along your element or along your column. So for the homework, I gave you this beam element, okay? I don't give you any fixity, right? I'm not telling you what boundary conditions are here. All I'm asking for is what is the energy equivalent nodal forces, okay? Because in the finite element analysis, right, we need to essentially tell the element what forces we have applied to it between known nodal values, right? So we essentially have to transform these forces that are acting between nodes to forces that are actually acting at nodes, right? So that the element knows what's going on between it, right? And so that's where this, let's see if we go back here. All right, in this case, we don't have a Q sub X, right? We don't have a traction force along the length, right? We have more of something like this going on, right? Except we have a point load. We have a point load that's acting some distance away. So from this, right, when we look through our derivation, we got our equivalent nodal forces. Right? This equation here. So these are nodal forces. So you need to evaluate whether we have nodal forces on our member. And then you take, okay, now I have our shape functions times our uniform load, right? And you evaluate this integral. And this whole thing here, right, becomes a 4x1. We're essentially giving a reaction in a moment at each of our two nodes that trick this element into knowing, okay, or telling this element what's going on between the nodes. So I just essentially want you to evaluate this guy right here.
So we are just solving that equivalent part, not the rest of it?
Yes, I mean, I asked you for F equivalent, so then I want you to.
Well, I just didn't know if like it was, again, like you could solve for it just from no.
Well, you don't know boundary conditions,
So
right?
you
So you
can't
have to
solve-
assume boundary conditions in
And we
order to
don't
make
know
this
that.
whole thing happen, right? And I didn't give you any of that. Just wanted to give you practice in saying, okay, this thing's kind of weird, we haven't dealt with this before, right? Okay, we've dealt with this, you can establish that, I give you K. D you can establish, you can partition the matrix, you can take the inverse, right? Figure out what our displacements are. But we need to know what forces are. Yes, Daniel?
Yeah, if you go back to
Homework assignment?
that P has
Something to do with the equivalent, energy equivalent force?
The P does, yeah. Because you can't, without imposing, right, forces in, like with respect to moment and translational forces, right, at the nodes, this element would have no idea that this exists, right?
So you input that one in the energy equivalent force as if you have a fixed beam, or how can you import that?
How can you import this? Well, if you looked at, right, a uniform load, right, if we looked at a very small sliver of this uniform load, right, giving you guys some of the critical part of this, right? If you sliced this uniform load up, right, and it's no longer a pound per foot, right? At one little slice, it's gonna have an actual pound, right? So it's essentially the same thing, right? Could be a uniform load, but it's only acting in a discrete location. So you can use the F equivalent integral, right? Shape function times, instead of W sub x, right? Now you have the magnitude, right? Instead of integrating over the whole length, right? Now you know where this thing is acting, right? And so you can figure out what's the contribution of P going on at nodes 1 and 2. You would add those up, right? If you had another point load, you'd have another contribution. If you had a uniform load that was only 2 feet of the length, and then you had another uniform load that was the end, right?
It's like acting over this infinitely small
Length,
length though, right?
yeah.
And then definite integral at the same bounds is 0. So it needs to be like
It
how
has
small and
it has no variation, right? An integral is the summation, right? From one end to the other. Right? You don't have to take a summation from one end to the other if you know that is the summation, right? Just P.
So could you do like an integral with W of x plus an integral with just P? It's not really an integral, it's just like.
Yeah, you would have a contribution from the uniform load, and you're gonna have a contribution from the point load, okay? We walk further through this? Yes, sir.
So you're saying because we don't have support conditions, we can't just jump into the beam tables and superimpose?
Yes, right? Because you don't know if this is fixed, whatever.
Yeah.
I just want you to tell me what the equivalent was. Yes, ma'am.
If you were to find like an equivalent line load that causes the same moment as P does and apply it across the whole length.
That's an interesting concept.
Would that like give you the same effect that each node?
It should, because, I mean, that's effectively what you're doing anyway, right? I mean, you're looking at reactions here and there based on taking this P and making a uniform load. That's what the equivalent uniform load does, right? I'll tell you, the point load's very simple, okay? Very simple. Right? It is a uniform load, but it's acting at one discrete point, right? So when you take the summation of it, it's essentially, or you take the integral of it, it's just P, right? One thing you have to think about, right? You still have the shape functions times that contribution, right? And so you need to incorporate those shape functions, right? Times that P, so you know that when this thing acts downward, right? It's going to have an imposed force, right? At 1 and 2, and an imposed moment. This P is going to want to rotate this as well. Okay. Are we square on what I expect? Okay. No, I mean, this is a good thing. This is a good thing. I'm not saying this is bad. Okay? Just want to make sure that everyone understands. Okay? Everyone's on the same playing field. Okay? Looking for F equivalent, right? I want you to evaluate that integral, right? That portion of our F equals KD equation. And you need to do that for the uniform load and the point load and add those together. And that matrix C, right, or vector you come up with is going to be a 4x1, which is R1, M1, R2, M2. Okay. Do you want to take your homework back, Daniel, now that you've had
Yeah,
this
I'm gonna
conversation?
finish that one. yeah.
Okay. I thought you might. Okay. Any other questions? All right. Has anybody listened to the? I mean, you guys have listened to the recordings. Can you hear me when I walk over here and?
It's quieter, but yeah.
Okay.
And you come back and it's really.
It gets loud and goes back again. Nice. All right. So that is our variational beam element. Okay. One thing I want to look at, right? We talked about how when we add axial loads, we assume very small displacements. Things get decoupled. I just want to quickly talk about, well, what happens when they are not small displacements, right? And now you start getting this increase in, right, or I guess coupling of the axial load to the bending moment, right? And what does that look like? So that was our variational beam element. Transposed it, or transformed it. So we're done there. Look at all these notes we've already done. Isn't that beautiful? Look at that. Okay. I'm excited for Adam's talk, okay? Something to think about for next Friday. Any question, right? There's not a dumb question to ask him. It might make you feel dumb after you asked it, but there is no dumb questions, okay?
We haven't used much VA.
No, I know, but anything, right? He's gonna talk about VA and his experience as an engineer, okay? Yes, Aaron.
Can you record that lecture?
Yeah, I was trying to think about how I could do that. I'm not sure what he's using to do it, and if he's putting stuff on the projector. I'll reach out to him and see if there's a way that he can record it for you guys.
Is this next Friday or?
Next Friday.
Friday before spring break.
Because next week's the last week, right? And then
Yeah.
spring break? Okay.
Then you're a week off. Just kidding.
Yeah, then a week off. Yeah.
You don't have your week off.
Whoa! Damn! Shit! Wow! Fucking ruthless!
You should end the semester a week early.
I should end the semester a week early?
Yeah, why not? Very good.
That sounds very tempting, actually. But the problem is I'm already here at 8 to 9, and so doing this class is fairly easy, right? It's just getting in line with doing it. Maybe we'll see.
And you know, I think the school gets mad when you don't even do finals during
Yeah,
finals week.
yeah, that was, whew. You guys could have all gotten me in trouble for leaving this class for sure. Maybe, maybe not, I don't know how pissed off Craig would have been, but. All right, so now we have, right, if we wanted to incorporate this idea of large deflections or think about this idea of buckling, right? Some instability that can occur based on like axial forces. Right? We consider a beam with constant axial force and a transverse load on it. Okay? And now we start looking at it in a displaced shape. Okay? We would have our axial force is constant on either side, right? P's. Right? We'd have this change in shear, right, which allows us to have a change in moment, right? M on one end, V on one end, right? And have some sort of area attached to that. Area is constant. And then we went to travel to the other end. Well, now we have this change in moment, change in shear. Axial stays the same. We'd have some change in displacement, right? We go from V, have some displacement at one end, and we'd have some change in displacement, right? Times some length would give us the change in displacement at the other end. If we sum moments, oops, erase, we get this dm dx plus, right, v minus, right, this is shear, minus p dv dx equals 0. Summing forces, we get dv dx equal to negative the load, right? If we're able to neglect shear deformations, we still assume that we have a slender member. If we have a slender member, we can still use our moment curvature relationship. Okay, where we essentially say, right, the moment equals to minus EI, second derivative of displacement with respect to X. Right, this is, sorry, V. Right. Well, if we differentiate M and then use the sum of the forces, right, we differentiate this, we get the change in shear with respect to X. So then we can plug the sum of the forces equation back into there. We end up with this. Right, so differentiate. Sum of the moments, and then use sum of the forces. We get EI, fourth derivative, with respect to displacement over the length equals negative the load, right? We know that. That's our typical differential equation for beam bending. But we end up with this extra term here, P times the second derivative of displacement with respect to X. So this is where we end up with this P delta coupling that occurs. Right.
Quick question.
Yes.
When you sum moments,
The term drops out. So like you use that, are you talking about shear?
I'm just wondering why there isn't a moment on for shear.
It's because everything drops. Like when you sum moments from one end to the other, you essentially, when you set it equal to 0, you pull out a common term between them, so you end up with just shear.
Okay.
So you use some of the moments, right? I was trying to simplify this. You use some of the moments across this cross section, and then using that equation, you can then simplify and drop terms out, and when you do that, this is the equation that you end up with.
Everything's multiplied by dx.
Yes.
It's meant to be over a small section.
Yes.
So it's just-
It's just a simplified version. I was contemplating when I wrote that to write the whole thing out because I didn't know if someone was going to catch it, and I should have known someone was going to catch it. All right. You guys need to be like Brandon, all right? Just absorb it, and then think about it later when I'm not next to you. Okay?
Then we can all make a line outside.
Then you can make a line outside my door. Okay. Mike keeps telling me, you know, you're just making this harder on yourself, right? Just make it easy, and then they don't show up. It's like, sure, all right, I'll do that. All right. All right, so we have this coupling. Well, we always start in our finite elements, right, with our displacement field function, right? We're trying to establish what's going on, a behavior between our nodal values. We use our shape functions to relate those nodal values to our deal. So again, though, same for previous beam. Our function now is a naught plus a1x plus a2x squared plus a3 x cubed, right? It's the same as we had for the beam. We have 4 degrees of freedom with respect to bending. We're going to have another degree of freedom, but that would also be use of x, right? We'd have to have this use of x value. And it's going to equal something. That captures our last 2 of those degrees of freedom. So we've got v sub x, it looks something like that. Right? Strains and strain energy, now we have to relate what's going on with respect to the strains to our nodal forces. Well, now we have 2 sources of those strain energies, right? We not only have the sources due to bending, right? We had this Hooke's law, area under the stress strain curve. Well, now we have this axial force, right, that we need to calculate, similar with what you guys did in the bar element, or your homework 4, right, where we had our rods, and you had the summation, or the integral over the volume of 1/2 stress times strain. Same thing happens here. Now we have to incorporate not only, right, now we have 2 sources of strain energy. We have bending. And now we have axial stress and strain, right? Due to P. Well, if we work through all of that, right, and we figure out what's going on with respect to our bending and our axial behavior, we can figure out our stiffness matrices similar to what we did, right? Strain displacement transpose. All of that good stuff, right? So the bending is stiffness matrix, then becomes the integral over the volume, BT E times B, similar to what we did, right? Just what came out of, whoops, equals. Okay. But now we have this axial contribution, which we call our geometric stiffness matrix, KGO, and the integral over the length, right? It's just acting over the length of G, this G matrix transpose times P, our axial force, times our G matrix. This is the derivative of N with respect to X dx. This is called our geometric stiffness. So when we get large displacements and we start looking at essentially P delta effects, right? We load it, it displaces, then we start this whole process over again, right? Establishing new forces, right? Incorporating new stiffnesses, which came from incorporating strain energy that now we have based on the fact that we have this axial load, right? That contributes to our overall behavior of our element. Right? So we end up with this geometric stiffness matrix. We look at a buckling problem. Right? Our total stiffness is our original bending stiffness plus our geometric stiffness. Well, when that becomes singular, right? You can't take the inverse of that. It becomes unstable. Right? You maybe have found that in VA before, right? Things are unstable, it'll say the stiffness matrix is singular, and some of the older versions have kind of changed over the years. But that's essentially what's happening is that either you don't have enough boundary conditions, right? You get either large, right, rigid body modes, right? You haven't even fixed your entire model and plan. You can just travel, you can cruise, spaceship around the Earth, okay? Or maybe one node or one element rotates, it's not fixed or it doesn't have restraint about it, so then you get this node that's spinning. We'll talk about that when we go through VA. Right? You might have this huge model set up and it's still saying that it's like unstable, right? It really pisses you off. You start going through it, combing through it. It might be just one node isn't connected appropriately to surrounding members, and so then it can just move. And that's a degree of freedom that VA or the computer model says, oh shit, when I invert this stiffness matrix, right, it's unstable. And I can't do it. Can't solve this thing. Well, for buckling problems, what ends up happening is we typically solve this without loads, because the way we look at it is the stiffness matrix plus the geometric stiffness matrix, right, times D. We set that equal to 0, because what we're really looking at is at what point does this geometric or the change in geometry overcome the original stiffness of the element, right, to begin with, or the system to begin with. So when this ends up making this singular, right, when you start adding in the geometry, then you have problems. And so that's why you pull, typically the solution for this is you pull out loads. Well, for some of you who took Mike's class, structural dynamics, this really becomes an eigen value problem. You guys remember that, right? Structural dynamics. How many was in structural dynamics? 4, 5, 6, 7. What set were you in there?
Years ago, 3 years ago.
Really? Wow, you were just
Forgot a little bit.
OG, huh? Just back in the day. So that means everyone else did really well because Sutton took it 3 years before. So it becomes an eigenvalue, eigenvector problem. Essentially, all that is it's a way of solving linear equations. And so what ends up happening is you get this equation where you have this eigenvalue times the normal stiffness matrix, and you set it equal to the geometric stiffness matrix. Okay. And you solve this eigenvalue problem, which essentially gives you your lambdas, which represent a set of n scalar, essentially these are our eigenvalues. Okay. And the largest of that eigenvalue is essentially the smallest critical load that the element can handle before it becomes unstable, before that quality becomes singular and you cannot invert it, okay? So largest, and that's all I really wanted you guys to get out of this, is that you get this geometric stiffness matrix that you then need to account for. Smallest critical load, right? So you get this geometric stiffness. So when you go in VA and you start a second order analysis, right, you hit the P delta button, right? So then it starts looking at the geometry as this thing displays. It steps through incrementally, right, solving it multiple times. I don't know if, Aaron, if you've gotten this. I've gotten it many times where I overloaded a structure and it does become unstable. So what VA will end up doing is actually scales the load back until it gets to a stable value. So at least it gives you something valuable out of it, saying, shit, I could only handle 1/3 of the dead load, right, before this thing became stable. Or if it can't handle it at all, sort of thing, right? It's like we did not hit a viable outcome, and if that's the case, then it's probably a boundary condition thing, right? So it gives you this ability of, is it based on the geometric stiffness, right? Is it this buckling issue that's happening? Or is it a boundary condition thing, right? So that's what I want you guys to get out of this.
Geometric stiffness relates to buckling, and the
Yes,
other one
and
relates to global stability.
The other one relates to, yeah, I mean, that's where your boundary conditions are going to be imposed in that as well. And so your K matrices is the stiffness of the undeformed geometry, right? The K geometric is the stiffness of your deformed geometry.
Right before.
Yes.
It's like
Well, so you don't know until you solve it, right?
It's like the controlling mode shape, for if you were to like it to what we do in structural dynamics.
Well, so when you do mode shapes, then it's an eigenvalue, eigenvector problem, and it's a bit different than buckling.
So it's not looking at which buckling pattern is going to happen.
No.
It's just looking at what point does it just follow.
No, because in there it's like, it's taking, in the resonance ones, right, the eigenvalue, eigenvector, it's taking into account natural frequencies, square root of K over M sort of thing.
So instead of looking through a ton of different mode shapes, it's just adding up. It's just going P times delta, P times delta, P times delta until that can't handle it and just falls over.
Yes. Yes. Where your scalars, the largest scalar value that it comes out of solving this equation is your critical buckling. So when you're going through it, VA is analyzing this, right? And if it analyzes at your imposed load value, right, and it is larger than the smallest eigenvalue, then it knows that it's instability. It essentially takes this and makes it singular, and it won't be able to solve it. Is it time already? Oh no, see, they got let out early. We got a few more minutes. Any other questions?
Did Adam Stordahl take this master's program?
Yeah.
And from there he went and all that stuff.
He actually worked at Morrison Merrily for a while. And then, yeah, he started working at IES, and then now he's one of the partners there. He bought into owning it. So, boy, genius. He's incredibly smart. He's a bright guy. He's a very nice guy. But like, and like, it could be any one of your guys' path, but he went to Morrison Merrily, and I don't know if, like, there's a church that sits across Main Street from the courthouse. Okay? It's a pretty large church. Well, Morrison Merrily did a big renovation of, like, the, I guess, chapel? What would you call, like, the big area that you sit in during?
Sanctuary.
Yeah, sanctuary, there you go. So in that, they redid the sanctuary, and in order to do that, they wanted a lot of glass windows. So they had these really big concrete shear walls, and you can ask him about it. Well, instead of just modeling that in VA, he took it a step further, went out to open source finite element analysis programs that incorporate nonlinear behavior. right? We've all talked about linear stuff, right? Hooke's law, right? So they're big concrete piers essentially coming out of the ground. So he decided to analyze it that way. So he was going, like, he just doesn't, that was his, he is in a great place now because he loves this stuff. Right? He really loves this stuff and the application of it. If I did that, I would never in a million years go out to some open source program out there to incorporate nonlinear finite element analysis of concrete, right? Which is crazy when it comes to nonlinear. So you get cracking, you have reinforcement in it, right? You got to come up with what's going on with, is the rebar yielding? Well, now it's the rebar's yielding is no longer linear elastic. So then the force that the rebar's putting into the system is going to be constant. But then you have cracking and degradation. So then you start shaking this thing in an earthquake, right? How fast does that concrete degrade and reduce the stiffness, right? When it starts out, it's going to crack so much. When it goes through one cycle, it cracks some more. Well, that cracking depends on how much displacement you have. People come up with ideas and models of how that degrades over time and you test them. So he implemented that as an engineer at Morrison Merrily. So that's just the bar here, right? When you guys are going out there and you're working for a firm, right? That's what he was doing. So he's where he needs to be, which is essentially developing software to help engineers out because he nerded out hard. You should ask him about that.
It's curious.
I never really talked to him about that. I just heard it.
He used the design earthquake, or did he use a special?
You could ask him.
cases?
And you could ask him. Right? Because if you do time history analysis now, you got to go out there and pick a suite. There's USGS allows you, helps you pick what earthquakes you need to hit it with, whether it's El Centro or something else. But yeah. Just when he comes in, everyone's just like nerd. I was always scared of him because he was like when I was in structures, he came in and he would teach lectures every now and then for Dan Van Lushen, and man, he's like one of those people that's like he's just like knows it too well, right? He just has this expectation that you are going to follow along faster than he thinks you will. I don't know. Just like, I get done with the class, I'm like, damn, what just happened? Hopefully you guys don't feel that way. All right, so Friday we will start with elasticity elements, right? Talking about plates, which will be fun because we're going to start talking about plates that are used in VA. We're going to talk about thin plates, and then finally at the end we'll talk about thick plates. Yeah.
Do you run P Delta on every model you do in VA, or is there like a certain?
I would run P Delta on, like if I was doing, so we'll talk about when we implement VA, but like column loads, right? They have the AISC, if you guys have all had steel 1 and 2 yet. Some of you have, some of you haven't, right? But in the stability chapter, they talk about you can do moment magnifiers, right? Those B1 and B2 values. Well, they also tell you now, they've incorporated a code, this direct analysis method. And in VA, there's an actual selection to do that. But what that's doing is essentially taking into account that if you have a system that is allowed to displace, right? If it's a brace frame or a moment frame, right? Do we have translation or not translation? And how that incorporates with respect to increasing axial or moments, right? Flexural demands and axial demands in the system. So if you check that box, the code allows you to do that. And you can essentially kind of wave your hands at doing the P delta analysis in the code because you're doing it in an analysis software. So you're not doing it by hand. And so a lot of times I do it for that reason.
Have you ever found that that you get P Delta failure before you hit like an interstory drift limit on a frame?
I mean, it's possible. I couldn't remember like the specific case that would happen, but yeah, I mean, that could happen, right? I mean, you just have too slender of members.
Yeah.
I assume it probably is happening in steel because it's such a strong and efficient like material that you end up not needing a whole lot of cross section, right, to handle the loads. But no, I assume that could happen, but I don't think of a case in particular that happens. So, okay. Friday.
You can use still on